Have you ever wondered why nothing, not even a rocket, can go faster than the speed of light? Let's break it down, with a little history, some physics, and a sprinkle of Einstein magic. Back in 1905, Albert Einstein published a groundbreaking paper titled, "Does the inertia of a body depend upon its energy content?" In it, he proposed something radical. Mass and energy are two sides of the same coin. That idea gave us one of the most famous equations in physics, E equals mc squared, where E is energy, m is mass, and c is the speed of light in vacuum. That's about 3 times 10 to the power of 8 meters per second. This means even a tiny bit of mass can be turned into a huge amount of energy. Take just 1 milligram of mass. That's 0.00001 kilograms. Now plug it into the equation. E equals mc squared, so that's 10 to the minus 5, times 3 times 10 to the 8th, squared. That gives us 9 times 10 to the power of 11 joules. That's about the same energy released by 200 kilograms of TNT from just 1 milligram of matter. Boom! In the early days of relativity, scientists believed that an object's mass increases with its speed. This was known as relativistic mass. The formula looked like this: mass equals rest mass, divided by the square root of 1 minus VE squared over c squared. As speed v approaches the speed of light c, the denominator heads towards 0, which makes the mass shoot toward infinity. And since E equals mc squared, you'd need infinite energy to keep going faster. That's why nothing with mass can reach or exceed the speed of light. But in modern physics, we've moved away from the idea of relativistic mass. Instead, we stick with the object's rest mass, denoted as m0, and it stays constant. So what changes as speed increases? Energy and momentum. Even when something is standing still, it still has energy. That's rest energy. E rest equals m0 c squared. Now, for a moving object, the total energy is given by this: E equals m0 c squared, divided by the square root of 1 minus v squared over c squared. This tells us how much total energy something has as it speeds up, and it brings us to an important insight. What if we try to make a rocket reach the speed of light? Set v equal to c. Then the equation becomes E equals m0 c squared, divided by the square root of 1 minus c squared over c squared. That's 0 in the denominator. And dividing by 0, that gives us infinite energy, which of course is impossible. So again, nothing with mass can ever reach the speed of light. Now let's get curious. What if you try to go faster than light? Then the term under the square root becomes negative. That would give us an imaginary number for energy, and that would imply imaginary mass, imaginary time, even time travel. Sounds cool, right? But sorry, those aren't real for objects with mass. So how do both views compare? In the old view, mass increases with speed. M equals m0 divided by the square root of 1 minus v, squared over c squared. In the modern view, mass stays the same, but energy increases. E equals m0 c squared divided by the square root of 1 minus v squared over c squared. Both lead to the same conclusion. You need infinite energy to hit light speed, so you just can't. Great question. What about light? What about photons? Photons do travel at the speed of light, but the key is they have 0 rest mass, so instead of E equals mc squared, we use this. E squared equals m0 c squared squared plus pc squared. Since m0 is 0 for photons, the equation becomes E equals pc. This means photons still carry momentum, even without mass. That's how light can push solar sails, trigger sensors, and even move particles in space. So let's wrap this up. Mass and energy are interchangeable. As speed increases, energy increases. At light speed, required energy becomes infinite. Nothing with mass can reach that speed. But photons, which have zero mass, can travel at light speed and still carry momentum. This idea is the foundation of modern physics, from nuclear fusion to particle accelerators, and even how we understand space and time. Pretty amazing, right?